Now I'm going to be talking about another approach for unsupervised learning, which is prototypical contrastive learning. So this paper represents prototypical contrastive learning, an unsupervised representation learning method that bridges contrastive learning with clustering. So it not only learns low-level features for the task of instance discrimination, but more importantly, it encodes semantic structures discovered by clustering into the learned embedding space. So we introduce prototypes as latent variables to find the maximum likelihood estimation of the network parameters in the expectation maximization framework. We iteratively perform each step as finding a distribution of prototypes via clustering, and M step as optimizing the network via contrastive learning. We propose Proto and CE laws, a generalized version of Info and CE. So we add another thing which is related to clustering, and that is the expectation step, because we consider those clusters as latent variables. So they propose prototypical contrastive learning, a novel unsupervised representation that bridges contrastive learning and clustering. So they give a theoretical framework that uses expectation maximization. And they propose Proto and CE, a new contrastive loss which improves the widely used Info and CE by dynamically estimating the concentration for the feature distribution around each prototype. And Proto and CE also includes an Info and CE term in which the instance embeddings can be interpreted as instance-based prototypes. And of course, it outperforms instance-wise contrastive learning. This is just the classical Info and CE loss that we represent it by some functions in this embedding space, but we also use expectation because our center clusters, those prototypes, are the latent variable. So they're unknown, we estimate them, and because this is an expectation maximization, this loop should go on until it converges. So we want to maximize this probability, but because we can marginalize this probability over many clusters, we can write this as this one, but we can use it as a surrogate function to lower bound it. So we lower bound it, and then we use the trick of Jensen inequality. So the only thing that we should maximize is this one. But in the expectation step, we estimate the probability of C sub I and xi. And we perform k-means on the features given the momentum to obtain k clusters. And we define prototypes as a centroid for the ith cluster. Then we compute it, and for the maximization step, based on expectation step, we are ready to maximize the lower bound. And using this assumption of uniform prior over cluster centroids, we set the prior probability is 1 over k because we don't know the prior, and we assume the distribution around each prototype is isotropic Gaussian. If we apply L2 normalization, then we can write this maximum likelihood. But in practice, we take the same approach as NC and sample R-negative prototype to calculate the normalization term. So this is the classical info NC, but we also add another term which is for those clustering. So another interpretation of PCL can provide more insights into the nature of learned prototypes. So this optimization it is similar to optimizing cluster assignment probability using cross entropy. And the linear classifier has a fixed set of weights as the mean vectors for the representation in each cluster. So it's just an expectation maximization loop. This is the expectation step that we find the latent variable, which is our clusters. And in the maximization step, we just try to maximize the loss of proto and CE, which is a sum of classical info and CE and the things that are relevant for clustering.